So, welcome back to today's video. Today we'll have a look at yet another application of matrix multiplication. This application will be an introduction to modeling, and what we will do is we will model the spread of an epidemic disease. Now, to say this beforehand, this model does not have a lot in common with the current ongoing epidemic, because we will make a number of simplifying assumptions here to keep things easy and to keep the focus on matrix multiplication. However, models like this, of course, form the very basis for more complicated, more complex models that take a lot more factors into account, and that can then be used to actually devise models that can help to predict and understand the spread of other diseases like the currently ongoing pandemic. So this is another application, and it's called spread of a disease. Now, as I said, our goal is to develop a simple model for disease spread in a fixed population. And we will make a number of assumptions here. And let's quickly sum up what we will assume. First, of course, we will only be interested in the number of healthy and the number of sick or diseased patients in the population. We will not be concerned with regional spread in this simple model. So we will only model numbers of healthy and infected people. We make a very simple assumption about the infection rate in this model, which is to say that each week 10% of the healthy population are going to be newly infected. We'll make an equally simple assumption about the infected part of the population, and that is that each week 20% of the currently infected population become healthy. So they are cured. Furthermore, our population is considered fixed, so there are no births and no deaths. And in particular, that means the disease is not deadly. So no one in our population is going to die from that disease. On the other hand, we will also assume that people do not acquire any kind of immunity once they have been infected. So a person that has been infected, then is cured, can become infected again. And of course, the question that we would like to answer is, how will the disease spread? How many people will be infected at a given point in time? Is the number of infected people going to increase, or is it going to decrease? Will we eventually have everyone infected, or will there be a point where that disease dies out naturally? And of course, on a larger scale, we'd like to know how this is all connected to the infection rates that we assumed here. So is there a way to avoid the worst case scenario, everyone becomes infected, by lowering the infection rate somehow? Because that is, as you know, that is what we are currently trying with the ongoing pandemic. So will that help with our disease? We're not going to answer these questions today, unfortunately. This is just a gentle introduction into that model, and we'll probably end up asking more questions than we are going to answer. But we take this as a first step. So we're going to pick up this model in later videos when we know more about the mathematics of matrix multiplications and matrix operations. And hopefully we'll be able to answer at least some of these questions later in that semester. So basically, the goal here, or the ultimate goal of this model, is to understand the dynamics of the disease. So how will our model look like? Basically, developing that model is the main step that we're going to undertake today. There's two parameters in that model, and that is, first, the number of currently infected people, and second, the number of currently healthy people in the population. And we call this dt, so that will be the number of people that have been infected by the disease at a certain time t, and we just use the number of weeks for t. So this is the number of infected people in week t. And then we also have the number of currently healthy people. We call that ht. So this is the number of healthy people in week t. And now we can capture the dynamics that we assume, the infection rate and the curation rate. We can capture that in simple equations. What we have then is the development of the population that attracts the disease, the infected people. Well, how many are those for a given week t? First, there's the people who have already been infected in the week before. Some of those will be cured, 20% to be precise, but the others will stay infected. So that means 80% of the people that had the infection a week ago will still have it. So that's 0.8 times dt minus 1. So that means 80% of people who had disease in week T-1, those will still have it in this week T. And then there's people that become newly infected, and we assume that 10% of the population that is currently healthy will be newly affected each week. So that means we add 0.1 times the number of healthy people in the previous week. So 10% will be newly infected. And of course, we can devise a similar equation for the number of healthy people. How would that develop? Well, 20% of the formerly infected people are cured. So that means the number of healthy people will rise by 20% times the number of formerly infected people. So that term here is at 20% of infected persons are cured. And of course, people who were healthy in the week before will hopefully stay healthy, with the exception of 10% that are newly infected. So that leaves 90% of the formerly healthy people that will stay healthy. So that's this factor here. 90% will stay healthy. And basically that captures the dynamic of our disease here. So let's try to write this in vector form. We'll introduce a vector pt, population at time t, that consists of the components dt and ht. Like this here. So we can then write the equations in the following form. Or we can say the population at time t, so the vector dt and ht, that can be computed from the corresponding population at time t-1 by just using these equations here. So we'll have dot 8 times dt-1 and dot 1 times ht-1 for the first part. So we'll have a matrix here, and we put a dt-1 and ht-1 here. And then we have to just put in these numbers in the first round. So that's dot 8 and dot 1. And we have to put these numbers here in the second round. So that is dot 2 and dot 9. And if we call this matrix here A, then what that means is, well, what we have here is A times P T-1. Or as a summary, PT equals A times PT-1. And that means if we know the current state, of course, we can make a prediction for the following week. Now, that's the easy part. But we'd like to make a longer prediction, and of course we can do this as well. if we know the current state, we can make a prediction for the following week. Based on that, we can make a prediction for in 2 weeks. Then we can make a prediction for 3 weeks, and so on and so on. So, hence, if we know an initial state, let's call it P0, measured at some time, we can compute PT for any t like this. So what we do here is, well, we say if we know P0, then of course we can compute P1. P1 is just A times P0. So that's what will happen next week. Based on that, we can compute what happens in 2 weeks, P2. P2 is A times P1. But P1 is A times P0. So basically here, we're using this. And what that means is, well, A times P0, that's the same thing as A squared times P0. And I guess you can already see where this is going. We want to compute the state in 3 weeks, P3. That is A times P2. So again, we just use this here, substitute it in here, and then we have A times A squared P0. So what we get is A to the third P0. And that means for arbitrary t, what we need to compute is A to the power of t times P0. So basically that A to the power of t will tell us how the epidemic behaves, how it evolves over the long term. So A to the power of t tells us how the disease evolves in the long run. So that's basically what we want to analyze. We want to compute this A to the power of t. And the question is, of course, how can we do that? Can we do that for arbitrary t? And then what can we say about that? And that's a question that we're not going to be able to answer right now. But let's take note of that for later. So the question is, how do we efficiently, of course, compute A to the power of t for arbitrary t? And even better, we'd like to say something about A to the power of t for t as it goes to infinity. So we'd like to have a look at the limits. Will that mean that the whole population is going to be infected? Will that mean the disease is going to die out? Will there be some kind of steady state? So something like 30% of the population will always be infected in the long run. Again, we have a look at this example later on to hopefully answer this question. For now, let's just have a look at one important point that might give you an idea of what could happen here. So for now, we consider one specific population vector P. We call it P star. And let's say we have a state of 1/3, 2/3. So 1/3 of the population is in state number 1. So that means, if you look at the vector again, that means state number 1 are the infected people. State number 2 are the healthy people. So 1/3 is infected, 2/3 are not. If we reach that state, then what happens with our disease at that point? Well, if we reach that state, then A times P star, if you just look at the numbers, let's substitute the matrix here. And then we can do the computations. What we get here is we have 1/3 times 0.8 and 2/3 times 0.1. So let's just put this 1/3 before the result. And then we get 0.8 plus 0.2. And for the second row, we get 0.2 plus 1.8. So that means what we have here is 1/3 times 1 and 2. Or in other words, 1/3, 2/3. And that's exactly P star. So you'll notice that if we reach that point, then you won't leave it anymore. So this P star is kind of a steady state, right? Once we are at that point, the relative sizes of the infected and the healthy population will not change anymore. 1/3 will always be infected at any given time. 2/3 will always be healthy at any given time. So the disease is not going away. It's not going to affect us all, but it's going to affect a certain number of people all the time. And of course, the only way to change that here is to change something about the parameters, for example, the infection rate. Then things might change for the better or for the worse, depending on what we actually do. So that doesn't really tell us how the epidemic will behave, but it tells us if we get to this point, then that's where we'll stay. Okay, so this P star here is a steady state. Meaning once the dynamics reaches that point, it will stay at that point. Unless, of course, there's some external effects that change the behavior, that change the matrix A, and then of course we will be able to revert from that point in one direction or the other. And by the way, a different name for that steady state, so this P star, this is called a fixed point. We talk about that in later chapters of this semester, but just so you've heard the name already, so this steady state is a fixed point here. Okay, this concludes today's investigations into this kind of model. Again, we haven't answered a lot of the questions that we posed. We will try to answer a few more questions in the future, but at least the steady state is hopefully getting you an idea of where this all might lead and how we can find this steady state and how we can prove that it's actually a steady state and compute it is something that will be reserved for future videos. So I'll see you in the upcoming videos.